Armstrong, Glenn, and Ames. We assembled an all-star team of external partners, including UC Berkeley, Stanford, Carnegie Mellon, and IBM, Almaden, and others. This team allowed us to train considerable expertise on this problem. So our project was aligned with Strategic Thrust 4, which is a transition to alternative propulsion and energy. Thrust 4 captures most of ARMD's activities in green aviation. Green aviation, of course, has the goals of zero emissions, low noise, and energy efficiency. A critical enabler for green aviation is our batteries. In this plot, we show energy requirements for electric aircraft. The major aviation battery requirement is high energy density. There are other important requirements as well, including rechargeability, safety, power, recharge time, and cost. In the figure on the x-axis, we plot the energy density of a battery in units of watt-hours per kilogram, and the figures give what technology that level of storage enables. The state-of-the-art rechargeable battery technology is lithium-ion technology. Lithium-ion is what's in all electric cars and consumer electronics, including laptops and cell phones. The current energy storage energy density of lithium-ion is about 180 watt-hours per kilogram at the pack level. It's the consensus view of the research community, however, that lithium-ion will max out at 300 watt-hours per kilogram due to fundamental chemistry limitations. The Boeing Sugar study and others have identified 400 to 500 watt-hours as the threshold for general aviation, and 750 watt-hours per kilogram is needed for more ambitious aircraft such as regional jets. Clearly, lithium-ion technology will never satisfy the significant requirements of electric aircraft, and so-called beyond lithium-ion technologies will be needed to enable this form of transport. I think it's fair to say that electric aircraft probably have the most extreme requirements of any battery application. We think that lithium-air technology is a unique fit for electric aircraft. For one reason, lithium-air has the highest theoretical energy density of any other battery chemistry just based on fundamental chemistry. And it's important to note to managers that there are actually very few alternatives to reach these very high levels of storage. There's lithium-air, there's perhaps lithium-sulfur, and you run out of options pretty quickly. So all of these have major challenges to enable electric airplanes. Lithium-air, in addition, we think has interesting synergies with aircraft. So for example, the aircraft have onboard oxygen handling systems that can be leveraged by lithium-air batteries to enable further mass reductions. These oxygen handling systems, of course, do not exist on cars, but they do exist on aircraft. However, despite its potentials, lithium-air has major challenges. For example, electrolyte decomposition limits both energy density and rechargeability. In addition, state-of-the-art electrolytes are flammable, which is unacceptable for cars and catastrophic potentially for aircraft. So therefore, we think that electrolytes, in particular, are the limiting factor for lithium-air batteries to achieve practical high energy densities, not theoretical, like I showed on the previous slide, but practical high energy densities, rechargeability, and safety. For our project, we had 4 technical thrust areas to work on these issues. First of all, we use predictive computation to accelerate the development of high stability materials and high performance cell and pack architectures. We also designed new material components and synthesized them and fabricated them for these high stability corrosive environments. We also tried to understand physics-based rules for decomposition. So a lot of why these components decompose is not well understood. So we think it's critical to understand the physics and chemistry behind this decomposition so we can design more stable compounds. If you don't understand why something's decomposing, how are you going to build a design around it? And we also wanted to look into some of the practical issues of integrating this technology with aircraft. Primarily, lithium-air has been an academic pursuit. We wanted to take the technology out of the ivory tower and look at some of the issues in inserting it in a practical engineering application. In particular, we think that our multidisciplinary approach where we integrate computation, synthesis, fabrication, and application engineering, is really what's needed to make rapid progress in complex technologies such as batteries. Here are some of the accomplishments that I'm going to quickly go through, just give highlights basically of each. We developed an extensive multi-scale battery modeling capability. We did fairly detailed evaluation of certain electrolytes that are promising. We went into a material design cycle 3 times, one to design what we call electrolyte stabilizers. We looked at, tried to design a high stability electrolytes and cathodes, and then we looked at some of the systems engineering issues as well. So let's look at battery modeling. So one of the accomplishments of the project was to develop a multi-scale battery modeling capability. This capability is very much in line with the Vision 2040 study, which was sponsored by TACP and T-Cubed. So I know we have John and Mike are both here, big supporters of this, and this is revolutionary, perhaps, impact it could have on development of not only materials, but of course materials, you know, applications are made out of materials. Everything's made out of something. So a lot of applications don't close the design because you don't have the right materials. So having a way to accelerate the development of materials that will close engineering applications is critical for advancing a lot of the technologies that we care about. We use predictive modeling at multiple scales to accelerate these development times. Traditional battery research has used highly empirical trial and error approach. But as I said, we relied heavily on computation in our project. So for example, we use high throughput screening of online databases. So there's these online databases that have potentially, you know, tens of thousands of materials in them. But we use computational screening to down select the most promising materials from these databases for this particular application. We also, and then we could, you know, try those out in batteries or synthesize them and then try them out if necessary. We also did high fidelity material simulations using high performance computers. This allows us to extract physics-based design rules for designing high stability materials for specific applications like these lithium-ion batteries. We also did multi-physics analysis to design high performance cell architectures, pack and cell architectures for this particular application. So all these were important aspects of our project. So the state-of-the-art electrolyte for lithium air is called DME. So that's the one here on the bottom. DME, you know, is one of those long chemical names that we all learn about in undergraduate chemistry. Is dimethyl oxyethane. It comes from a class of organic electrolytes that are based on ethers. Now, ethers perform well in lithium air, and they're viewed as an alternative to the carbonates, which are what people usually use in lithium-ion batteries. But these do not really get us to the performance that we need for aircraft or any real practical application. So we wanted to look at 2 other classes of organics, namely ones based on ureas and amines. So these are ureas here and these are amines here. And so we evaluated these 10 organic electrolytes to determine their stability and try to look at trends in their performance. So for each of these 10 electrolytes, organic electrolytes, we evaluated what we call the oxygen recovery efficiency. And basically what that is if you have a lithium air battery, the way a lithium air battery works, so that's up here, when you discharge the battery, you consume oxygen, so oxygen is drawn into the battery and consumed, and then when you charge the battery, it's exhaled or it's expelled. And so you want the amount of oxygen expelled to equal the amount of oxygen that was inhaled or consumed. And if those numbers should be equal to each other if you want to have a rechargeable technology. If they don't equal to each other, that's going to reduce your cycle life. And so ideally that ratio is going to equal 1. And so if the amount recovered is the amount that was consumed, you get a ratio of 1. So on this chart here, you see these are the oxygen recovery ratios. And that ratio will basically determine how many cycles you can get out of the battery. So for example, if you wanted 100 cycles, which is one of the targets of our project, it requires a 99.9 efficiency for this oxygen recovery ratio, which is actually huge, right? That's a very demanding constraint. For DME, for example, you know, we come in about 90%, so 0.9%. So obviously that's not going to get you significant cycle life. So that's why DME basically dies after about 4 or 5 cycles. So we evaluated these other organics, and we got these. Now, some of these actually failed quite spectacularly. These are DMI and DMPU, but we did find 3 that did better than DME. And Now while these did better than DME, they still didn't reach these 99 plus efficiency that you really need for a practical rechargeable system. So this wasn't going to be the final solution for us, even though this is an improvement over DME. So another part of the analysis we went into was, why do these things decompose to begin with? So we wanted to understand, what is the decomposition chemistry for these systems? And so we were able to identify the reactants in the products. So the reactants, for example, is the solvent molecule, and the products are in red here. And if we know the reactants in the products, then we can postulate a possible decomposition mechanism. And if we understand the mechanism, then we can try to design around it. Now, interestingly, this decomposition mechanism initiates with a nucleophilic attack on the CO bond here, double bond here. So what that means is the CO double bond is the weak link of the solvent molecule where the initiation starts. So therefore, design strategies can involve, for example, either replacing that weak link or protecting that weak link from further decomposition. So again, the message is if you understand the physics and chemistry, then you can get into design. But if you don't understand, then you're sort of tossing darts in the dark. Another thing we looked at is electrolyte, we call electrolyte stabilizers. Now, one problem with these batteries is that a lot of the oxygen under charge gets locked up in lithium peroxide particles which accumulate on the electrode surface. And so when you charge the battery, you want to release the oxygen, but if oxygen gets locked up in these particles, then you can't release it, and that reduces your efficiency. So the only way to get this out is to drive up the cell voltage, and by driving up the cell voltage, you initiate further decomposition, so you're kind of in a bad loop here. However, if you introduce additives to these systems, these so-called stabilizers, these stabilizers can facilitate the release of oxygen without increasing the voltage and therefore initiating further decomposition. So you get no decomposition but higher efficiency. So we looked at different ways to do that. So we looked at this class of molecules. This is what we call a tunable class of electrolyte stabilizers, and this class that we looked at is based on this molecule of thianthrine. So thianthrine is very interesting for several reasons. One is it has nice electrochemical properties, but it's interesting structurally because you can attach things to it, and you can attach different things to it. So for example, you can attach oxygen or bromine or methanol or all kinds of things, and then depending on where you attach different things in different places, you can tune the properties. So these give you several designs, several knobs to turn to tune the properties. Now, if you think about all possible things you can attach to just to this one basic molecule, then that's a huge design space. So you say, well, how am I going to pick what to focus on? Well, of course, the answer is computational screening. So we use computational screening to down select the best candidates out of this design space, and then we synthesize those and evaluated those in batteries. And what we found is we actually found it actually worked, and we actually got a 2x improvement in cycle life, which is encouraging. However, for these systems, we actually need orders of magnitude improvement. So even though 2x is good, it's not good enough. So we think that these stabilizers are interesting and worthy of further examination. However, this does not by itself represent the final solution, but it might be part of a final solution. So we did a lot of work on organics, which I just showed, and then we said, well, what about inorganics? So if the organics aren't working for us, let's try inorganics. So we tried these molten salt electrolytes, which are known for their high stability properties. Molten salts, for example, are used in nuclear reactors and also in thermal storage. And so we tried these as electrolytes. And in this figure here, what we're plotting here is we're comparing the organic DME versus one of these molten salt electrolytes, and we're plotting efficiency here versus cycle number. So as you see, the efficiency changes as you go the number of cycles, and DME, as we expect, dies after about 4 or 5 cycles. However, if you continue now over the molten salt, which is the red curve, actually you can cycle 25 times. So here we found a 5x increase in cycle life with the inorganic molten salt versus the state-of-the-art at DME. So this was encouraging that we got a 5x cycle life. However, we were a little bit perplexed because we didn't really see any evidence of decomposition of the electrolyte, but yet we only got 25 cycles. Why didn't we get 100 or 200 or 1,000? And what we found out was the problem was with the cathode. So it turns out that the cathode we were using, which is made out of carbon, a standard lithium-air cathode, actually has decomposition problems of its own. So as you cycle the battery, you get these parasitic product, this lithium carbonate, these little red nodules that form on the electrode surface. And as you continue to charge and discharge the battery, these red things accumulate until they completely cover the surface of the electrode and basically stop the battery. So the bad thing about these carbonates is they're electrically insulating. So if you put an electrically insulating layer on an electrode, you basically kill the electrode. So these things are dying not because of the electrolyte decomposition, but because of the cathode. So not only do we need a high stability electrolyte, but we need a high stability cathode. So we went looking for cathodes. And of course, you get ideas. We went to the computers again to try to get some ideas. And so we went back to the databases online, and we looked tens of thousands of candidates. We did material screening for chemical stability, electrochemical stability, absorption characteristics, et cetera. And then we down selected the most promising candidates. And we were actually quite excited about some of the candidates we found, which were based on so-called transparent conducting oxides. And one of those is zinc oxide, which is shown here. So we show the phase diagram, which we computed. And this indicated that this should be very stable. There's a whole family of oxides that are potentially stable. And so we tried these. We put these in batteries and we tried them. And another nice thing about these is that we can is that there's a lot of different ways for fabrication, and there's morphologies that we can do in different surface areas, which are advantageous. But unfortunately, these didn't work. And these are one of the last things we tried before the end of the project. And so not only did we try zinc, we tried antimony, indium, et cetera, and there was unexpected parasitic processes that were basically killing the battery after one cycle. So there's something here that we don't understand that requires further work. We still think these materials are promising, but more work needs to be done to understand what this parasitic process is. So the last thing I'm going to show you is one slide on our battery pack. So I told you that lithium air has mainly been in the ivory tower primarily. So you have all these professors at universities wanted their papers in Nature. And so we actually wanted to build a pack and see how it performed in electric aircraft situation. So we built this pack. Here's 5 cells, 12-volt pack, weighs in at a trim 300 grams. And we basically ran it through its paces. So this is a simulation basically that we did using the pack, a laboratory simulation. So here's a profile that our friends from Armstrong gave us for aircraft. So here's a 1-hour flight. And here's the power profile here of taxi, takeoff, cruise, descent, and landing. And we ran the pack through this scenario and had no problem executing this trajectory, albeit at a very low power rate. So the conclusion is that the pack actually worked well for what is needed for electric flight profile. However, further work is needed to increase the power levels, the specific power and the volumetric power levels as well. So the conclusions is we think that with its material design approach that I've shown several examples of, that we identified a promising path to extended cycle life and higher practical energy densities involving alternative electrolytes, stabilizers, and new cathode materials. We think lithium air is viable for electric aircraft. I think really the main purpose of this project was to assess, is lithium air viable at all, or are there showstoppers? We did not find any showstoppers for lithium air. So therefore, we think that it is worthy of consideration, given its enormous potential, very high energy densities, and very limited other options. So again, to make this point, there are not that many options to get you to 500, right? Lithium air, lithium sulfur, and that's about it. Maybe some others, but that's kind of it. So lithium air, you got to face it. You got to face the music. However, so we think it should still be on the table for further development. However, and here maybe the VC should cover your ears, so Peter, don't listen to this part. Lithium air is still fundamentally a low TRL technology, and significant development is required for it to be deployed and real applications. That means significant investment by investors and funders and significant work by researchers like us. We think NASA can and should contribute to battery development in general for aircraft. This is not being addressed by DOE or industry, who are focused on battery cost and safety for cars, not for aircraft, not high energy density for aircraft. That's not their focus area. We believe that a multidisciplinary approach combining predictive computation, material synthesis and fabrication, battery engineering, and application systems engineering is essential to make progress in this area. And with that, I will stop. So what happens?
He's here, so he's gonna.
Do I sit down now, or what do I do?
So you can sit. Yeah. You're gonna answer questions.
Oh, I have to answer questions?
So PK is gonna run the Q&A session. PK, you wanna do this, or you want me to do it?
Sure, I can do it.
All right.
So we have a new member now, Sarah. So Welcome, Sarah. Would you like to introduce yourself?
Yeah, absolutely. Hi, I'm Sarah Childs. I'm from. Is it? Push. Okay, now you can hear me. I'm Sarah Childs. I'm from Starburst. We're an aerospace and defense focused accelerator and Series A level VC. I'm based in LA, but we're actually operating in 8 countries now internationally. And so what we really do is act as kind of the intelligent matchmaker between startups, small business, and the large corporates that potentially would want to be partnering with that technology. And there's a lot more to that. We deal a lot with technology transfer and helping to give technical co-founders the business acumen they need to be able to commercialize their technology as well. So we run multiple accelerator programs internationally, and yeah, that's kind of our domain expertise.
All right, thank you. So who wants to go first? So, go ahead. You want to go first, Viren?
No, go ahead. I think you had a question.
Oh, well, I can ask John. John, what was the most exciting part of this activity when you got started?
I think it's just we had a remarkable team. So I think
Push the button there. So
Yeah,
yeah.
I think we had a remarkable team, and we were extremely excited about the team. And we knew it was a super hard problem, but we had a super strong team, so we thought we could take a good shot at it, and I think we did. I think what I showed you is a wide-ranging tack on this problem, and some things work, most things work, some things didn't work. Almost everything needs more work, but yeah, I mean it's always fun to work on hard problems. With smart people. I mean, that's why we became researchers to begin with, right? To solve very hard problems and work with the best people in the world. So I think this project was an opportunity to do both of those things.
So with respect to the computational technologies that you developed, can you talk a little bit about how specific they are to this battery problem versus how generalized they are for all types of materials problems that people might want to go and solve in the future? And, and like a roadmap for extending this capability.
Yeah, no, that's actually a very important point. I'd say almost all the tools are general purpose tools. I say most of the tools we use, I don't know if we can put a slides, can we put slides back on? There's one slide. There's like slide. So I'm going to put a slide, go to the front. Can I control this? So this is, this is what we did here for this project. But this is I mean, initially wanted it to be battery agnostic, but it's actually application agnostic. So here, this is aligned with the Vision 2040. A lot of what's called for, Vision 2040 report, which I was part of the team that developed that. And this is like a massive report that gives a true roadmap for how to do this for all kinds of materials, right? And so a lot of what we did is sort of in that spirit, although we have our own spin on that. And so, things like doing, high throughput screening, there's all these databases online. People, one thing people talk about all the time is let's do machine learning, right? Okay, well, so that's great. We should be doing that. But another thing to do with data is just screen data. And with computation, you can actually fill out databases. So these databases, a lot of times, they're incomplete or they don't have the properties you want. But coupling a database with a computational engine, you can actually fill out the database and actually do screening that way. So sort of do virtual screening with virtual data, not experimental data. And then actually you can have like some sort of an Uber data set where you have experimental data and computed data. So now you have an even bigger data set to do other things, to do more machine learning and data science and all that kind of stuff. With all this data and screening stuff, this high fidelity material simulations, we have one of the biggest supercomputers in the world, and here at Ames, it's available to everyone at NASA. It's a huge resource. We can do some of the best, and we do some of the best and biggest and best, supercomputing simulations of materials, in the community. And we do things that no university can compete with just because they have their small clusters, but we have tens of thousands of nodes, whereas universities might have hundreds of nodes. And so we can do extremely high detail, large, complex simulations that many people can't do. Also, multi-physics and multi-scale analysis, atoms, ultimately, you don't want to simulate every atom, in a battery. I mean, because that would blow short circuits all over the planet, right? So you need some way to couple at scales, like how do you couple the atomistic scale to some continuous scale, which is where you're doing like finite element modeling, for example, of a battery, right? But that battery doesn't have to be a battery. That could be a semiconducting device. That could be a whole airplane. We could be designing structural materials for an airplane wing. So that could be a finite element simulation of a wing, and we could be designing Aerobond. I don't know if Frank's here, but we're part of Aerobond. There's Frank. So we could be designing polymer matrix composites and non-adhesive interfaces, and then we can plug that into some weighing actually and do the whole simulation. So that's sort of the broader vision is we want to couple everything together as part of the design. So structures, devices, you name it. Is that too much, too little, wrong direction?
No, I think it's good. I mean, one of the things that comes to mind is that there are aspects of these batteries that have inherent instability in terms of how they charge and discharge.
Mm-hmm.
And the instability and the difficulty in predicting how that plays out in a given battery cell is part of what makes this technology so challenging.
Correct.
And so on the one hand, okay, if we can model that in a simulation system at high fidelity, that's part of the battle. But can you categorize in what instances that insight gives you real levers to build a better battery and how that part of the process plays out? Because we might develop a really high fidelity picture of, yeah, this is not a stable system and it's just difficult. It's just going to be difficult to make it work,
Yeah.
versus those insights that allow you to address that at the core and come up with a design that doesn't suffer.
Yeah. No, I think this is the only way you're going to solve the problem. But I don't think you have a choice. I mean, it's not a choice. You have to do it like that because if you don't understand what you're doing, then how are you going to design something that you have confidence in?
Yeah, if you can't measure it.
Or if you have, I mean, if I'm going to design something, if I'm trying to find a solution to an unstable system, if I want to have confidence that it's going to work, I want to understand the instability and know that my solution actually solved the problem, right? So that's what has to do with these batteries. These are chemical. These aren't mystical instabilities. I mean, it's basic chemistry, right? There's chemistry. Things decompose all over the place all the time, and sometimes it's a good thing, sometimes it's not. In this case, it's not a good thing. So using basic computational chemistry, we have computational chemists here in this office. I saw Harry walk in, so we have at least one computational chemist here, who people have been working on problems like this for generations, and so there's a lot of expertise that can be leveraged to solve these problems. So it's not like we have to start from zero. There's a lot of experience out there in the community. All we have to do is pull it all together. And I think that that's something that our group has done. I think fairly successfully. Is we think that chemistry is important for materials. A lot of people who do computational material science only model the materials, but we actually think that chemistry is important for materials. So we have computational chemists in our materials group because we think chemistry is important for things like this, for decomposition of components and things like that. So you have to understand what's going on before you have a bright idea to solve the problem. Now sometimes you can automate solving the problem, right? So sometimes you can hook it up to like some optimization scheme and say, okay, well let's cycle through, let's connect our screening, our high throughput screening, and say, okay, if we know some mechanism is operating, some chemical decomposition mechanism is operating in the system, let's introduce all these other different molecules. Instead of having that one molecule, let's put all the other possible 10,000 molecules in there and see if all of them decompose in the same way. Maybe some of them won't. If they won't, then those are candidates that we should look at in more detail. Or maybe we're just have an Einstein moment and we say, okay, well, I think if we built another molecule based on my insight, I can design something that will not decompose according to that mechanism that I found. But if I don't know the mechanism, I don't have a chance. Otherwise, I'm just throwing darts. And that's that's why batteries are decadal and generational to make progress, right? Because that's a lot of empirical. There's a lot of smart people working on it. A lot of people have smart ideas. But the more you understand, the bigger acceleration, the more acceleration you can have in that process.
So given that there is a tremendous amount of funding going on from VCs in the battery work, what do you see the potential, or have you seen anything like this in the outside world, or do you see touch points or any guidance for him where we could actually figure out more relationships outside NASA or try to develop partnerships in transition paths?
So one question I had was the specific technology that you have developed. I assume the inherent value proposition is at the high end of the transportation food chain, aircraft and things like that, or do you think this has benefits even in automotive or even other areas? Because energy harvesting and storage, even for the small devices,
Yeah.
is something that people are trying to solve.
If we can get this to work, everyone will use it.
Yeah.
It would replace lithium ion.
Yeah.
Yeah.
So
The question is, so you could say, well, why aren't people doing that? I say, well, it's expensive and it's hard and it's decadal, it's generational, and it requires consistent investment. You don't just do it 2 years then drop the ball. You continue to invest it, sustained investment over time.
yeah,
And so people, the automobile and consumer electronics industries are completely in on lithium ion because that's
Yeah.
mature, stable. They understand it. They don't need 400 or 500 watt hours per kilogram. Tesla with 180,
Yeah.
you can get almost the same distance as my gas powered car. So would it be nice? Of course, it'd be nice, but do they want to do decadal investment? For that extra few miles? It's not the value. I get the value proposition. What we have now is good enough, as opposed to the scale of the investment that is needed to get longer range on a car. But for airplanes, I mean, if you can't even fly more than 50 miles, then you have then your vision is dramatically restricted in what you're going to be able to achieve.
so it is at the higher end, yeah. It
Well,
makes-
that's what will drive the development. But if you can make this work, then the cars will use it immediately. Of course, yeah. But the car companies are not going to invest in this
Yeah.
because they have a solution that works.
It seems that
Would they like a better solution? Of course, but they don't want to pay for it.
it seems that this type of capability would allow the battery industry to develop and push forward a greater diversity of battery chemistries in parallel rather than continuing to do incremental work off of things that are already existing and mature.
Yeah.
Yeah.
I agree with that.
Yeah, John, I don't know if you're familiar with Ampere in Southern California. They do regional. Right now, they're retrofitting regional aircrafts right now, but
Okay.
they're a portfolio company of ours, so I'd be happy to kind of intro you there. But in terms of my understanding of lithium air, the nominal voltage is lower than most lithium-ion batteries. Is that correct? So you have to line up more in series, and
So it's higher. The voltage is higher. So
the voltage is higher.
it's not a lithium ion. I guess it depends on what you mean by lithium ion. But traditional lithium ion batteries have lower energy than lithium air.
Oh, my understanding was the opposite. Okay, never mind then. So then in terms of charging and discharging, are there any advantages that you see there? I think that's one of the greatest barriers too, is there increased charge time?
Well, that's actually a good question. That's kind of unexplored at this point because right now we're just having trouble recharging the batteries at all. Because the nice thing about lithium ion is that you can recharge them hundreds or thousands of times, which is terrific. Which is why everyone uses them. However, these right now with the standard electrolytes are 4 or 5 times, which is not practical. I mean, you can make these into a primary battery, but with a single use. But we already have better primary batteries that work. So getting them to recharge at all is the challenge probably for this technology. It's the number one challenge. That's what we spend most of the time focused on in the project, trying to get them to recharge more times. But because of this decomposition, like what Peter was talking about, all this decomposition that degrades the battery as you're using it, and then finally just fails because of the accumulated degradation. And so trying to contain that degradation to like fractions of a percent or less, is really the challenge. Even to get to 100 cycles, you need 99.997%, non-degradation recovery. If you degrade more than 0.0003, then you can't even get beyond 100 cycles. So even getting into recharge is a question. How fast it recharges, well, that's a second level thing to think about. If it doesn't recharge at all, then we don't think about how long does it take at this point. But that's something that'll be important in the future, though.
Any question, or should we go to audience? There's a bunch of questions for you, John. The first one has to do with problems with electrolytes, additives, cathode materials from sustainability and environmental perspectives. Maybe that's too early to start to think about it, but have you given any thought on sustainability issues?
Well, I think compared to lithium ion, it's probably a better situation because lithium ion, we have these, especially the cathode sides that are very difficult to recycle. And here the cathodes are very simple, it's just carbon, oxygen. So in fact, from that standpoint, it might be a better technology as far as recycling.
That's good. All right, thank you.